My invisible friends, hello, and welcome back to our series on electrical engineering. Tonight our conversation is about the BJT and small signals, and we begin remembering how a diode behaves in front of small signals. The diode is connected to a linear circuit inside that gray box. The linear circuit can be characterized by a Thevenin equivalent with a Thevenin voltage and a Thevenin resistance. The current in the diode and the voltage in the diode is what we want to find. The current in the diode is the current in this resistor, that is V Thevenin minus V diode divided by R Thevenin. That is the relationship between the current in the diode and the voltage in the diode as given by the linear circuit. We have not considered the diode yet, but whatever ID and VD are, they have to respect this equation. That equation on a plot of ID versus VD is a line. It is a straight line with a negative slope 1 over RTH that has a value when VD is 0 of V Thevenin over R Thevenin, which is the short circuit current of the linear circuit, and intersects the horizontal axis when ID is 0, VD is just V Thevenin down here. That line that is imposed on VD and ID by the linear circuit is what we call the load line. That is the equation of the linear circuit. But the equation of the diode is one we know pretty well. It's an exponential. That says that whatever we do, ID and VD must fall within the curve described by this equation. This one, this exponential. That gives us only one possible solution for that system of equations, the intersection of both curves. That intersection presents what we call that the resting point of the circuit, the quiescent point, the Q point. At that point, we can read VQ and IQ, which are the actual voltage of the diode and the actual current in the diode. We call those IDQ and VDQ. Let's include now a small AC signal that is in series with a DC signal V Thevenin. Small? Yes, small in comparison with V Thevenin, the DC source. The effect of having that extra small additional voltage on top of V Thevenin will be the oscillation of that load line around the Q point, like that. And then the voltage in the diode will also oscillate around VQ, and the current in the diode will oscillate around IQ. We need to find the relationship between the voltage oscillations and the current oscillations, and that is the purpose of this conversation. Let's concentrate on that in this curve. We care, I repeat, for the relationship between changes in voltage and changes in currents due to the presence of that AC source. In this Zoom, I have emphasized the delta ID and the delta VD. They are related by the slope of the tangent to the exponential curve and the Q point. That is the one that gives us what is the relationship between delta ID and delta VD. Because we know what is the current in the diode as a function of the voltage in the diode, we can find the derivative, and the inverse of that derivative will give us the relationship between delta VD and delta ID, which is a resistance, right? Voltage divided by current. That resistance, delta VD over delta ID, turns out to be N times VT, the thermal voltage, divided by IQ, IBQ, the current in the diode in DC, the current in the diode at the quiescent point. So this tells us that for the AC signal, the diode looks like a mere resistor with the value RD. We call RD the dynamic resistance of the diode at the point of operation Q. Let's do a numerical exercise. Let's say that we have that circuit where we have one diode, the linear circuit VC and R Thevenin, and an AC source, a small signal. We solve that circuit using superposition. We solve the circuit first with a DC source. We short the AC source, and we solve the circuit as you have seen me do that in class very often. And then the representation of the circuit in AC. We kill the DC source we shorted, and we draw the circuit the way the AC signal sees it. This is a short R-Thevenin, continues to be there, but the diode looks like a resistor up here, RD. That is the circuit seen by the AC signal, the small signal. The solution to the circuit is a superposition of this solution and this AC solution, both for the current and for the voltage down here. The actual voltage in the diode has a DC component VDQ and an AC component lowercase v, lowercase t. The same is true for the current. Now we have refreshed our memories about small signals and the diode. Let's carry that over to the BJT. I leave that exercise for you to practice at home. In the BJT, we remember ourselves that the BE junction, the base emitter junction, is a diode between the base and the emitter. If it's a diode, then the relationship between this voltage in the diode VBE, the base emitter, and the current in the base, they have to follow the exponential formula of Junction, right? So that has to follow that expression. The base current depends on VBE according to that exponential formula. Where is N? N is 1 for the transistor. We have only the thermal voltage VT and the saturation current I naught. If the base emitter voltage has a small AC component, which is the point of this conversation, then the total voltage based on the emitter will have a DC component that we know how to compute and an AC component. The superposition of both of them is what gives us the total answer. This is the DC component of the current in the base, and this one is the AC component of the current in the base, given by that very simple relationship. From that, we extract what we call the AC or small signals model for the BJT. Take one. This model is perfect for the common emitter configuration of amplifiers. We have one resistor and one dependent current source. The terminals of the transistors are the base, the emitter at the bottom, it's a common emitter, and the collector on the top right. That is VT divided by IBQ. And we apply the AC voltage, lowercase v, lowercase be, and we get an output current. That is beta times IBAC. This is the AC component of the base current. And beta times that AC component of the base current gives us the AC component of the collector's current. In this example, we're not considering yet the early voltage. That is for later. Many researchers call RBE R pi, and they call this the pi model of the transistor. They prefer in those cases to represent the current in the collector not as a function of IB, but as a function of the AC voltage between the base and the collector. It is very easy to make the translation. R pi is the same RB, which is VT over IBQ. This formula, GMVBE, has to be equal to beta IB. It is the same current. VBE, that voltage, the AC voltage applied between the base and the emitter, is IB, the AC base current, multiplied by R pi, or RBE. So that means that IB is this AC voltage divided by R pi, or RBE. That is the replacement there. That's telling us that GM has to be beta divided by RB or R pi, however you want to call it. That is the pi model of the BJT. That is very appropriate for cases in which the transistor is connected as part of a common emitter amplifier. Here, this is a summary of that. VBE, this is an AC signal. VCE is the AC output of the transistor. R pi is the input resistance, that is VT over IBQ, the base current at the quiescent point, and GM, the transconductance, is beta divided by this R pi. And so much about that. Let's move on. Let's talk about James or Jim Early and his voltage V sub A. This is supposed to be a subscript. We estimated before that the output characteristic of a BJT would be something like this, would be a combination of an infinite number of horizontal lines that begin at VC 0.2 volts and they extend themselves to the right, one for each value of the base current. That gives us what is the collector's current. When we went to the laboratory, those lines did not look quite like that. They were not horizontal. They looked like this. They were slanted. They suggested that the current in the collector at any of these lines is the sum of two currents, a constant one and a current that is proportional to the voltage between the collector and the emitter down here. The current in the collector is the sum of the constant term beta IB for any one of them, beta IB is constant, 40 microamps or something, plus another voltage that is proportional to the voltage VCE. And then the current in an unknown resistor connected across C and E, because in that resistor the current would be proportional to the voltage VCE. So we needed to expand the equivalent circuit with the insertion of that additional resistor. We need to add a resistor R0 in parallel to the control current source. What should be the value? That was the question, until James Early realized that if we extend all of those slanted lines backwards, they intersect the horizontal axis at the same point. That suggested that at any value of the base current, the appropriate resistor would be the same, and that resistance would be the inverse of the slope of the corresponding line. The slope of that line at any value ICQ would be approximately the rise ICQ divided by this voltage VA. The inverse is the resistance R0, VA over ICQ. That's how we compute the additional resistor of the small signal model of the transistor connected in a common emitter configuration, R0, the early voltage, divided by the quiescent value of the collector's current. The pi small signal equivalent, again, it's perfect for common emitter configurations. I've said that. The small signal equivalent seen so far is called the pi circuit, and it keeps the emitter connected to ground as common between the input and the output the emitter is. It is also drawn sometimes like this. Observe, the emitter is at the bottom, the base is on the right, and it's separated from the emitter by that resistor R pi, same as before. The voltage VBE, lowercase, that is an AC signal, is between the base and the emitter. That hasn't changed. And then between the collector and the emitter we have the same two branches, this source and this resistor. It is the same circuit drawn slightly differently. But that is not the only way of representing the BJT in AC. No, this is good for cases in which we have a common emitter. But when we have a common base, which is not that often, but when we do, because it's an important configuration, then it's better to use the T equivalent for the transistor in small signal analysis. This one. That T is this one. You say that does not look like a T. Well, imagine we are not considering the early effect, so this resistor would not be there, and then we say that looks like a sidewise T. This is the head of the T. This is the the body of the T. You say, oh, I see, that is a T circuit. Yes, that's right. Why is this resistor R pi divided by beta plus 1? The reason is simple, you see. The voltage difference between the base and the emitter, VB, has to be the same in this model or in the pi model before. But in the pi model before, that voltage was R pi times I beta. Now, the resistor is drawn on the emitter branch, and in the emitter branch the current is beta plus 1 times larger. If we want to have the same voltage, it has to be, then the resistor has to be beta plus 1 times smaller. Let's do the math. VB used to be RB IB, which is RB multiplied by the base current, can be written as the emitter's current, divided by beta plus 1. Let me move the denominator over to the resistance and say that voltage is also the emitter's current multiplied by RB divided by beta plus 1. That's why we divide R pi, which is another name for RBE, by beta plus 1. Let's look at an example that comes out of one of your assignments, assignment 7, question 10. The transistor is in common base. You say, how is that? Look, the base is connected to the reference, to ground, and so is the input and the output. So the base is common to the input and the output. This is in common base. This is a perfect case for replacing the transistor BJT for its equivalent T circuit. The input signal arrives in the amplifier at this point, and the emitter, and the output signal comes out of the collector and out to the load through this now shorted capacitor. Input and output. Input and output. Remember that. Eh? Let's redraw that. A common base example, the one we had in the previous slide. In AC, that circuit would look like this. Vs, our source, there. They are connected to the emitter. What happens to this source? It's DC. So in DC, there is an open circuit between the emitter and ground. So it is not there. It would be between the emitter and ground. But it's open. It is not there. And then we continue into the transistor. And the transistor is represented by a T circuit. Here we see that it really looks like a T. This is the resistance, which is our pi divided by beta plus 1. And this current source that is GMVBE. There. The directions are from collector to base for the current. The polarity of the voltage will be for VBE. Higher at the base, lower at the emitter. That is a convention. The resistor of the collector is connected between the collector and the ground, because now VCC is grounded. There is this one. This capacitor is shorted in AC, and we have finally the load resistance. There, that is your circuit. By the way, you can see immediately that the input resistance into the amplifier, that begins here. This is the source. This is the amplifier, begins there and ends here. This is the load. Looking into the amplifier between E and ground, all we see is this resistor, R pi emitter, which is R pi divided by beta plus 1. And on this side, if we look into the amplifier, into the output port here, all we see between that point and ground is this resistor RC. Good. Let's apply the small signal model to a common emitter circuit like this one, that one. First, I encourage you to solve the circuit in DC. That will involve only those 4 resistors, the source and the top 15 volts, and the transistor. From there, we will find what is IBQ, the current here in DC. That is IBQ. With IBQ, we compute the equivalent base emitter resistance in small signal, RBE, which is VT over IBQ. And then we can draw that circuit in AC, like this. Look, I invite you to explore the AC equivalent circuit and compare that to the actual circuit and come up to your own conclusions. And that is all, my students, for now. Thank you very much, and I hope to meet with you again in our next video. Uncut.